Okay, so let's go through this application exercise. So the first thing I'm going to do is add my name as an author. So I'm going to put myself in here as an author of this document. And I've copied the questions in here from the slides, so we've got that set. Okay, so the first question says, 5,000 women were enrolled in a study and were randomly assigned to receive either letrozole or placebo. So either a treatment or placebo. And the primary response variable of interest was disease-free survival. So when I copy in this table, it looks a little bit messy, but if I knit this, it looks better. So I'm gonna go ahead and do that. Yeah, so there we go. So we've got this nice table here. Let me pull it so we can see the whole thing. Okay, so we've got, oh, the table's a little bit off. Hold on, let's fix that. We need to put in an outcome there. All right, so our outcome is death or disease, and we've got in the treatment group 185 with that outcome, 2,390 without it, and for a total of 2,575. So the first question asks me to calculate the odds ratio of death or disease in the placebo group versus the treatment group. And so that means that the numerator is going to be the placebo group, and the denominator is going to be the treatment group. All right, so let's do this in R. So the first question is going to be the OR for the placebo. And so for that, I'm going to take 341 divided by 2,241. And I'm going to divide that by 185 divided by 2,390. Okay, so the odds of death or disease, let's copy this into the actual spot where it belongs here. So the odds of death or disease in the placebo group are, I'm going to show you a fun trick here. I'm going to save this as OR1, so for the first odds ratio. And what you can do is you can actually insert R code into your R Markdown documents by using this backtick and then the letter R and then whatever code you want to run. So here, I can actually insert the actual values so I don't have to write it myself. And it will just insert it into the text automatically so that if I change this answer up here, it'll change this value down here. So this is kind of cool. Okay, so the odds in the placebo group are 1.96 times higher than in the treatment group. And actually, I'm going to go ahead and just round this so that it doesn't end up having a whole bunch of decimal points. Okay, so let's see how that looks. So I've got my code here, and then I say the odds of death or disease in the placebo group are 1.97 times higher than in the treatment group. All right, my next question is calculate the odds ratio of no death or disease in the treatment group versus the placebo group. So now I'm calculating the opposite in two ways. I'm flipping what my outcome is, and I'm also flipping what my referent category for my exposure is. And so if I use the numbers in this table, I'm going to end up doing 2,390 divided by 185. So this is the number of no death or disease in the treatment group versus death or disease. And then I'm going to divide by 2,241 divided by 341. So this is no death or disease for the placebo group versus death and disease. Okay, so this is my OR2. And I'm going to use this same, but now we're doing the odds of no death or disease in the treatment group. This is going to be OR2. All right, so let's see what that looks like. pull this over here. All right. And so now you'll notice that these two numbers are the same. And so what this is driving home is that when you flip both the referent category for your outcome and the referent category for your treatment, so since we flipped both of these referent categories, we end up with the same number both times. And you can look, I mean, algebraically it makes sense because this is just 341 over 2,241, which is the inverse of our denominator here. And when you divide by something, you're dividing by, you end up multiplying by it. So this is sort of like flipping this. Dividing by it is the same as multiplying by the reciprocal. And same here in the numerator here, it's just the reciprocal of the denominator. And so these two equations are going to end up giving us exactly the same answer. And so when you're calculating an odds ratio, the referent categories are important because they dictate kind of how you're thinking about these values. Okay, so the final question is to calculate the odds ratio of death or disease in the treatment group versus the placebo group. And this is the most common way to think about this. This is usually how we think about these questions. Usually we think about them in terms of the odds ratio of the disease outcome and comparing the treatment group with the placebo being the referent category. So for this, it's going to be 185 divided by 2390. So this is the number in the death or disease cell divided by the number in the no death or disease cell, both of these in the treatment column. And then we're going to divide by 341 divided by 2,241. So the number for the placebo group. And so for that, we end up with 0.508. And so now the odds of death or disease in the treatment group are this times, and we're going to get rid of higher, the odds in the treatment group. So now let's take a look at that. And so now that 0.51 ends up getting populated there. Great. All right, so now the question, the last part says, using the default data from the ISLR package, fit a logistic regression model predicting whether a customer defaults with whether they are a student and their current balance. So I've added some code here to load these packages. I'm going to name this chunk. Actually, I'm realizing I need to name these too. You want to make sure your chunk names always need to be unique, so I couldn't name these two chunks the same thing. It won't run if you do that. All right, so we've got our data loaded, we've got our library loaded, and so I want to fit a logistic regression model. And I'm going to set my engine as GLM. Oh, and you know what? That reminds me, we need to load the tidy models package too. Okay, so we're going to set the engine to GLM, and then we're going to fit a model, and it's going to be default. I'm going to make this, I'm going to set my message equals false, warning equals false in this chunk so that when we run this code, we don't end up with all of that text in the output. Okay, so fit default is going to be equal to student plus balance, and the data is going to be default. Let me make sure that's the right way. Let's take a look at the default data set to make sure those are the right pieces. So let me pull this over so you can see. Yep, default, student, and balance are the names of the variables. Okay. So let's run this code, make sure it works. Looks good. So what I actually want here is I'm interested in the actual parameter estimates here. And so I'm going to do that. I'm going to use the tidy function. And here I get these estimates here are on the log odds scale. And so I can interpret, for example, this one I can say a 1 unit increase in balance yields an expected change in the log odds of default of 0.0057, holding whether or not the customer is a student constant. So that's on the log-odds scale. I think it can be hard to interpret things on the log-odds scale. It's not super intuitive what it means to change default on the log-odds scale by 0.0057. And so often when we are doing logistic regression and we're trying to interpret the coefficients, we are going to use the exponentiate, the exponentiate equals true option. And so let's make sure we do that right. Let's see, exponentiate equals true. All right, so now we've exponentiated these values. And so instead of that 0.005 that we saw before, this is taking the exponential of that, which is 1.0057, which is exactly what we see here. And so now we can say a 1 unit change in balance yields an expected 1.0057-fold change in the odds of defaulting, holding whether or not you're a student constant. So if this were on like a lab or something, you'd want to write out that full explanation of exactly what this means. You'd want to make sure to say holding student constant because this is multiple logistic regression, and so it needs to be explained in the context of the other variables. All right, so I'm going to go ahead and knit that. Oh, let's name this chunk. Let's knit that up. And I'm going to show you one other trick after we knit this. Okay, so now we've got this code down here, or this output. And I'm going to show you one other trick for cleaning up your output. If we add, there's a function in the knitr package called cable. And the way that I'm calling this is instead of running library knitr, I'm just saying, since I only want one function from this package, this double colons here, this basically will call a single function from a specific package. It would be equivalent if I added library knitr up here, and then I could just use the function. And if you'd prefer to work like that, that's totally fine. Sometimes if I'm using a function just once, I'll just do it like this, where I write the package with the colons. So this cable function is really nice because it basically cleans up your output to look like a nice table. And so when you're doing things in reports, it's a nice way to be able to show a nice clean table. So here I'll show you what that looks like now. So now in our output we've got this nice table instead of that kind of that computer output that we saw before. It looks a little bit nicer. All right, so there you have it.